This is applied physics course for undergraduate students, and today we start the chapter 5 applications of Newton's laws. I would first go through a few important concepts, and then we'll do a few examples. In this regard, action and reaction example is shown here. The normal force table is exerting on the monitor. This N, the table force on monitor is shown as Tm, and the reaction, uh, this force is a normal force. It means it is perpendicular in this case, and the action is actually the earth that is exerting on the monitor, and earth is exerting a force of equal and magnitude and the opposite in the direction to the reaction force, and this force which the monitor is exerting on the earth. The force on the object, if we look at the free body diagram, we can see a normal force and the force which is the table force on monitor, and there is a force which is due to the gravity, and it is the earth force on the monitor. So we model here the object as a particle, and the normal force and the force of the gravity are the forces that are acting on the monitor. Free body diagram expression is very important in describing all the mechanics. Before we start using the Newton's law, first we draw the free body diagram in which the object is shown as a point particle, and the forces are then shown in the vector form along x-axis and y-axis. Be sure to include only those forces that are acting on the object of interest. And we can include any force acting on the object, but we will not assume that the normal force is equal to the weight. It is it is the reaction. So the force due to the gravity is the force which is exerted by Earth on the monitor. The particle model is basically used to represent the object as a dot in a free body diagram. The forces that act on the object are shown as forces applied on this point or dot, and the free body diagram helps us to isolate only those forces that are acting on the object and eliminate the other forces from the analysis. If we look into the analysis of the model using the Newton's law, we assume few things first, and the object can be modeled as particle is the first assumption, and we look at only the external forces acting on the object. We can neglect the reaction forces, and initially we will be dealing with the frictionless surfaces, and the masses of the strings and the ropes will be considered as negligibly small. The force on the rope exerted is always away from the object and parallel to the rope. Similarly, when we have the rope attached to an object and is pulling it, the magnitude of that force is the tension in the rope. So if the acceleration on the object that can be modeled as a particle is zero, then that object is said to be in equilibrium. The model is a particle model, and the particle is in equilibrium, that model we are considering. Mathematically speaking, the net force acting on the object is zero, then the vector sum of the forces, that is the sum of all the F vectors, is equal to zero, which means the sum of the all forces in the x direction and sum of all forces in the y direction are zero. Then let us consider one example on this equilibrium. A lamp with the shade is suspended from a chain of a negligible small mass, and it is connected to the ceiling. The forces that are acting are shown here. The downward force is the force of gravity, and the upward force is the force of tension in the chain. And these two forces, we can see the tension force and the force due to the gravity, as shown here on this lamp. And the upward tension is, of course, away from this object. Then we have only the y component of forces. So therefore, we balance this and say that the sum of all y component of the forces is equal to 0, which means that the T is in the positive y direction. It is taken as positive, and F due to the gravity Fg is negative because it is downward in the decreasing values of y. So it is minus and it is equal to 0. Therefore, the tension is equal to the force of gravity. Now, we must keep in mind that if object is experiencing an acceleration, then there must be a non-zero net force acting on it. And model of particle then will be under a net force model. Still, we can draw a free body diagram, and then we can apply the Newton's second law in its component forms to reach at the further conclusions. If we look at the usefulness of the Newton's laws, let us do this simple example of force acting on a crate. Here, a person is pulling a crate, and with the help of a rope, and it is a straight horizontal motion. The tension acting through the rope is of magnitude T, and the gravitational force is force Fg, and the normal force acting on the object due to the floor is N. So if we draw the free body diagram, we have this coordinate system, X and Y coordinate system, and the crate is shown as the dot. The normal force is in the upward Y plus direction, and the F due to the gravity is in the downward direction with the negative Y direction, and the tension is in the horizontal direction, and it is the leading force. So applying the Newton's second law in component form as sum of all the horizontal forces, the X components are equal to the tension only, and according to the Newton's law, this tension is equal to mass time acceleration. Similarly, the Y component of the forces are net forces are equal to N minus Fg, and it is equal to 0. The minus sign is due to the fact that it is in the negative direction of Y, and from here we find the N is equal to Fg. This is not producing any acceleration, therefore this was termed as 0. And we can then find that the normal force is equal to the force of gravity, and solving for the unknown, the tension. If the tension is constant, then acceleration is constant, and the kinematic equations can be employed. Now, let us very briefly talk about the normal force again. Let's see that this is a table on which a physics book is placed, and a force F is acting downward due to my hand. Hand is placed on the book, so it is exerting a force. However, there is a normal reaction of the table to the book, and it is normal force N. And then there is a force due to the gravity. This is Fg. So in this case, all the Y component of the forces are such that the N is the normal force minus F G, you can see it is downward, and the force which is being applied by the hand is also minus F. So the normal force is equal to the mg plus F, and therefore this shows that the normal is not necessarily always equal to the force of gravity, and it is less than Fg, the force of the due to the gravity. It is there is a force, which is applied force. So you can see that uh, uh, we can not always equate that the normal force is actually equal and opposite in the direction of Fg. And this is the real true definition of the normal. Normal force is here sum of the forces. The further forces are acting, and the normal is the reaction of all those sum of all those forces that are acting and opposing the this going down in inside the table, and the normal forces to resist this action. Let's briefly discuss the problem solving hints using the Newton's law. First of all, we draw a diagram, normally a free body diagram, and then choose a convenient coordinate system. Then categorize, is this model a particle model in equilibrium? And if this is the case, then the sum of the forces is equal to 0. And we can have the components in x direction and in y direction and in z direction. And if the model is a particle model under a net force, then the sum of the forces is equal to mass time acceleration. And then we can solve this further to find out the velocities and the displacements. So analysis of such problems include a free body diagram, include only forces that are acting on the object. We apply appropriate equations in the component forms. We solve the equations for unknowns, and then we finalize the results. We check our results for consistency with the free body diagram, and we would like to make sure that there is the results are physically realizable, and the problem is solved. Let's do one example in which the tension and the normal forces are involved. Pulling one crate is being done under the force P, which is applied on a string over a surface. And the force on a crate is exerted by the string, and this force is tension. Now you can see here in the diagram that this is a crate, and there is a rope attached, and the man is pulling it with the force P. The crate, if it is thought to be a point, then the crate and the rope has this free body diagram that the crate as a point, and the tension T is the net force which is acting on it. Now, if we look at the string somewhere here, then this string is a point on which the away from this point is the tension, and the string is being pulled by the force P. Now, keeping in view this x coordinate and y coordinate of the system, we write down first the net force on the string in x direction. You can see here the string is this, and it has sum of all forces along x-axis equal to P minus T. P is in positive direction and T is in the negative direction, therefore P minus T has been written. Furthermore, we write P and T that are the magnitudes of the P and T, and we know very well that the second law says that this is equal to mass times the acceleration if there is a net force. But when there is no net force, string is there and string is not getting detached and it is not accelerated, then it is equal to 0. If this is the case, then the force which is applied on the tension, creating a tension, then this force is equal to the tension. Then we go further to the crate. Now, if we look at the crate, the force on the crate is only tension. The sum of all the forces is equal to the tension, and it is equal to the mass of the crate times the acceleration, and therefore the mass times acceleration of the crate. This is equal to tension. But from the previous equation, we know very well that the tension is equal to the applied force. Therefore, this acceleration basically is equal to the applied force divided by the mass of the crate. And that's how we reach at the conclusion. So a systematic problem solving in mechanics, it can be done like this. Let's extend this problem further to the two crates that are being pulled. Now look at the first crate and man. There is a rope. Man is pulling it with the force P. The mass is M1. The mass M1 is attached to M2 through a rope. And once this mass starts moving, then there is a tension in this intermediate rope and it pulls mass M2. So first we look at the mass M1 and then we look at the mass M2. Let us look at the mass M1 and balance the forces. The first force is the tension T1, which is away from this mass. And then there is a tension T2, which is again away from this mass. It is T2. So force on the string, we know very well here that the force on the string is, as usual, the tension minus the magnitude of the force P. And according to the Newton's law, this is equal to mass time acceleration, and this is equal to 0. If this is the case, then we can say that the tension is the T1 tension is equal to the force applied force. Now we move to the crate 1, and the crate 1 has this T1 minus T2. T2 minus sign comes due to the fact that it is in the negative x direction. So T1 minus T2, and T1 is equal to P. So P minus T2 is equal to M1 mass multiplied by acceleration. So we can write M1 AX equal to P minus T2. This is the final equation for the crate 1. Similarly, for crate 2, we can write with the net force in the x direction is T2, and that is equal to mass time acceleration. Therefore, mass time acceleration is equal to T2. M2 times AX is equal to T2. So if the string does not stretch, then the both masses M1 and M2 are moving with the same velocity and the acceleration. Therefore, A1x is equal to A2x equal to AX, and therefore we can reduce the equation M1 AX equal to P minus T2 and M2 AX equal to T. And we can simplify these two equations to reduce them to AX equal to P divided by M1 plus M2, and T2 equal to M2 times P divided by M1 plus M2. So here we can see that the acceleration is actually the total force as if it is acting on the sum of the two masses M1 and M2. And the tension in the second string is the fractional force, which is M2 divided by M1 plus M2. So a problem solving has been done using the free body diagram for mass M1, free body diagram for mass M2, and then for the string, and then simplifying the equations. So we begin with this problem and simplify and identify the variables here. This is a sample problem in which the figure is showing that there are 3 ropes they are attached at this point or node, and then there is a mass which is attached to this string C. So A and B and C, three strings are employed, and these three strings have the mass M2 attached. Both A and B strings are attached to the ceiling, and the angles subtended are 45 degrees and 30 degrees. Question is, the block's mass is 15 kg hanging from these three strings, then what is the tension in these three strings? Solution is that we first of all write down and consider the knot. This knot at the junction of these three strings, and here we draw a free body diagram for the knot, which is at rest under the action of all these three forces. We have these three tensions. If we look at the knot, away from the knot is the tension TB, away from this knot along the A string is the TA, and similarly away from this knot in the direction downward is the tension TC. So we resolve these three forces TA, TB, and TC into their X and Y and components, and we know that if this angle is 45 degrees, then this angle is also 45 degrees. Similarly, if this angle is 30 degrees, then this angle on along the horizontal x-axis is also 30 degrees. And the component, we can decompose a vector into two parts. Along the x-axis, it will be the cos, and along the y-axis, the component will be the sine. So the horizontal component of TB will be TB cos of 45 degrees, and the horizontal component of TA will be TA multiplied by the cos of 30 degrees, and the vertical will be TB sine of 45 degrees and TA sine of 30 degrees. So if we have done that, we can write down the sum of the x force components as a minus TA times cos of 30 degrees. We know that this side, this direction, the decreasing x value will be the minus direction. So TA cos of 30 will be minus, and TB cos of 45 will be plus. Similarly, the sum of the forces along y will be TA sine 30 degree will be in the upward direction, and TB sine 45 degree will be in the upward direction. But the TC has no component, horizontal component, but only vertical component, so it will be minus TC. Once we have done this, that the net forces have been found, then the net force along the x direction is equal to mass time acceleration, and the net force along y direction is the mass time the AY. So this sample problem up to this point is clear to us. Now we can use these two equations further to find out the unknowns. Because the acceleration is zero, this knot is not moving anywhere. Therefore, you can write down this equal to zero and substitute the angles and calculate the values. So if we reduce this, we have these two equations. We must keep in mind that the block M can also be a node, and on block there is a force away from this in the C rope, which is the tension TC, and there is a weight downward. So we can write the sum of the forces along y direction for the block M as TC minus M into G, and this is mass time acceleration, which is equal to 0. By substituting, we can find out the value of TC, and then from above two equations, we can find out TA and TB values. Remember, in mathematics, we know whenever there are three unknowns, we need three equations. Whenever there are two unknowns, we need two equations. Here there were three unknowns, tension along this rope A, tension along the rope B, and tension along the rope C, TA, TB, and TC. And in this case, we had this equation, third equation for the block. And from this equation, we find TC. And from above these two equations, we can then find TA and TB. I think we stop here, and in our next lecture, we will see how further we can solve the problems using the Newton's laws. Thank you so much.